rectangle is on the curve. Now where the finger is pointing is off the curve, but what I'm looking at is over here on the curve, and press enter. And so I'm using the leftmost endpoint of this subinterval. What is the value of that? Well, let's see. For the first rectangle, we would have 0 plus 1 minus 1 times a half, or 0. Is that in fact the coordinate of the leftmost endpoint? And in fact it is. If we build the second one, we want to go for the second rectangle, we would have 0 plus 2 minus 1 to the 1/2. That would be 0 plus 1/2, or simply 1/2. If we look here and build a rectangle now, starting at this point and going over, and I want to come up to where it's on this curve again, what is the leftmost endpoint of the second rectangle? And it's at 1/2. And we can continue doing this then for the rest of the rectangles. If we are using the right endpoint, so we were just working on the left endpoint and we were using this. If we're looking at the right endpoint, we're going to have to compute the value we're using just a little bit different. And so for the right endpoint, we're going to use A plus I delta x. In this case, that's going to be 0 plus I times 1/2. And so now for our first rectangle, we should have 0 plus 1 times 1/2, or 1/2. Let's go back over here. If I now take a rectangle, and I'm going to go back here, over to here, but now I use the right endpoint then to determine my height. The right endpoint of the first rectangle is going to be at 1/2. The right endpoint of the second rectangle is going to be at 1. So let's see if we get that. For the second rectangle, we would have 0 plus 2 times 1/2, or 1. And again, that would be the rectangle, the smaller one here. So we have now rectangles that come above the curve. These would be called circumscribed. And those we're using on this curve, those we're using the left endpoints of our subintervals here. If we're using the inscribed ones, those that are the rectangles lie completely under the curve, we have to use then the right. Now this is going to change according to the function. So we have to know if for the function, if we want to be above the curve, we have to know which endpoint we're going to use. Okay, so this part says determine the left and the right endpoints of our intervals. Now, in order to calculate the lower sum, now the lower sum is going to be what we consider to be the inscribed area, or inscribed rectangles. This is going to underestimate the area. The lower sum is the minimum of the function there. So to calculate the lower sum, we would need to use the right endpoints of each of these subintervals. If we're going to use the upper sum, which we have over here then, the upper sum is going to overestimate the area. These are going to be circumscribed rectangles. And so again, for our to be certain to have to overestimate, to use those that come above it, we're going to have to use then the left endpoints for each of these rectangles. Okay, so to calculate those, what we would need to do then is to set up a summation, and this is the part that I'm not going to hold you responsible for. I want you to understand what we are doing with our two sums here, but I'm not going to hold you to having to go through all the summation piece of this. Instead, if we are looking at, let me continue with our work here, and we go to rectangles, and I use the left endpoint to determine. Again, that's going to overestimate. If I do the same thing but use the right one, it underestimates. And we'll do the last one, and we will find that rectangle, and then we'll do this one. So we've got some that overestimate and some that underestimate. If we look at the area of this, and I use the larger rectangles here, we would need to sum those up, and I hesitate to go through all the steps with you at this point. However, it's really not that difficult. If you followed what I was doing there, I went to menu and measurement and picked up area, and then I just pointed to all of those rectangles. Now, to add them up, I'll go through this with you. Go to menu, go to actions, and we first need to type a text. And so I'm going to type a text. We have 4 rectangles, so it'll be A plus B plus C plus D. And press enter. Now I need to use that expression to pull these values together. So I take menu, actions, and I do calculate, and when I point to the expression, it's going to ask me what is the value A. I point to the each of these areas in turn, and I get an area of 435. Now, the other rectangles, of course, are the lower ones here. So I would need to go back and do a measurement of area on those and place those areas accordingly so I can keep track of what they are. And then if I go to menu, and I think what I will do is type a new text here, and we'll just somehow, let's say A1 plus B1 plus C1 plus D1, and press enter. And we'll just try and keep track of which ones those are. Menu, actions, calculate. I point to this one, and it wants to know again what values I am wanting to use here. And now if I look at these, I can see that my overestimate is greater than my underestimate, which is to be expected. What we can do, of course, is to use more rectangles, which is going to increase our calculations. Now, if you want to replicate what I just did, I drew the rectangles, I went to menu, went to shapes, and I can then do rectangles. There may be some error there because if I did not get the point right on the function, it may not have attached itself to that. And so these may not be as accurate as they need to be. They are only estimates. Okay, moving forward in our notes, compare where we found that the overestimation, of course, is greater than those underestimations. What would make it better if we have a larger number of rectangles? Of course, going to infinity would be the ideal, which is where we go to then. Our theorem 5.3 basically is saying just that. That if we look at the limit of the, as n goes to infinity, the sum of under the curve, if we look at the limit of the underestimated area, so this would be the underestimated area, and we take the number of rectangles to go to infinity, that would be the same thing as the overestimate of the area. And so if we basically just take the summation as 1 goes to n, and n is going to infinity, of the, now keep in mind, this is the height of the rectangles, and this is the base of the rectangle. So together, this is the area of rectangles. Then we would be able to get a very, very, very accurate, almost exact value of that. Okay, let's look at this problem. Determine the limit of the summation of all those rectangles as the number of rectangles goes to infinity, and we are given this. Now, if we think of this as delta x, and we think of this then as the summation as I goes from 1 to n, if you look back, you'll see that this is Crawford and Gauss's. This is adding up numbers from 1 to n, integers, that is, whole numbers. What the problem is asking for, the limit as n goes to infinity of 18 divided by n squared times this n, the quantity n plus 1 divided by 2. If we consider that 2 divides into 18 9 times, and n squared can have a common factor that we can cancel out. We could say that this is, well, let's start with n divided by n squared times n squared plus n, which would be the same thing as the limit as n goes to infinity of 9 plus 9 divided by n. Now, as n goes to infinity, go back to our work in section 4.5, as the denominator increases without bound, the value of this fraction becomes 0. So we have 9 plus 0, or simply 9. So the summation of this quantity, as we allow n to go to infinity, is just simply 9. And again, that may not be problem 33. Okay, this next problem says use the summation formulas to rewrite the expression without the summation notation. That is, rework this so that we end up with something that does not use the summation notation. Well, basically, what I want to pull out is the fact that the index is j. J is the one that's varying from 1 to n. J is the, for lack of another word, the variable here. N squared is a constant. And so we end up here with 1 divided by, that's that scalar, times the summation as j goes from 1 to n of 4j plus 1. Now, if we bring that, and we'll bring that down here, we can now write this as 1 divided by n squared times the summation as j goes from 1 to n of 4j plus, remember we can break these apart, the summation of a summer difference is the summer difference of the summations, j going from 1 to n of 1. So we have 1 divided by n squared. Here we have another scalar, so that's 4 times the summation as j goes from 1 to n of j, plus, now this is that constant, and remember we can reduce that down to the constant times the number of terms. That's back on the first page of these notes. So we've got 1 divided by n squared we have 4. And now this term right here, this is the Carl Friedrich Gauss